Well, this is sort of my way of assuaging some guilt for having driven a car that consumes gas for over 65 years. And this is an adventure. I'm going to take you on a little trail where we're going to discover how to measure Earth fever. And I'm going to take you down the trail that I followed over the past year. So it'll be fun because I'm going to share with you both the history, some history of science, as well as my path towards discovery. Let's see. I advance here. Now, when we talk about a fever, I'm looking at this as a physician. We look at the cause of fever. Why does a person have a fever? And the cause is related to what we call pyrogens. Pyrogens are substances, polysaccharides that come from bacteria and fungi and viruses, and proteins that come from cells within our body, the monocytes and the macrophages that are found primarily in our blood, but also in our liver and our lungs. And these pyrogens, these chemical substances, travel to a central point of control for our body temperature. And that control point is in our hypothalamus, kind of right deep in the center of our brains. And the brain responds to this stimulus by actually allowing our muscle to contract more vigorously. And you know, when you get a fever, if you get a chill, you start shivering. That's the hypothalamus at work. And the hypothalamus also does something else that is actually mimicked by Gaia, and that is it contracts the surface blood vessels. So when somebody is developing a fever, you may look at them and they look kind of ashen and pale. Well, that's because their little blood vessels that go to the skin have little muscles in the arterioles that contract. And by doing that, they don't allow us to dissipate our heat. Let's see. Now, it's easy to determine a fever in a human because we all have the same temperature. One person to another, from morning to noon to night, doesn't matter the time of day, we have basically the same core temperature in our bodies. No matter what environment we're living in, if we're in a jungle in Costa Rica or off the coast of Alaska, our body temperature is going to be the same. And also from one season to another, whether it's summer or winter, our core temperature is very much the same. Now, we use a simple thermometer, and now, of course, they have digital thermometers, but in order to measure our temperature, this, what can I say, is actually fairly recent. It wasn't until 1724 when Daniel Fahrenheit, a scientific instrument maker in the Netherlands, actually designed a glass bulb thermometer containing mercury to measure the body temperature, and then he named a scale, the Fahrenheit scale, using 0 as a combination of ice and salt. That was his 0 point, and he wanted to set 90 as the human temperature, body temperature. He used the axilla, the armpit, as a body temperature. He didn't quite strike it right, but anyway, very close. And that's the Fahrenheit scale. And we still use the Fahrenheit scale was used primarily by physicians back in the 18th century to measure body temperature. And now here in this country, we're still using it. The rest of the world adopted a more scientifically designed scale to measure temperature. And we're now thinking in terms of scales and measurements. We have to have a scale if we're going to make measurements. And the Celsius scale is based on freezing at the point of 0, the point at which water freezes into ice. And then 100 on the Celsius scale is the point where water, a liquid, changes to a gas, the boiling point at sea level. So, and we can measure the fever very easily with humans. Fever being 99.5 Fahrenheit or 37.5 centigrade or Celsius. Anything above that is a fever. Now, the pyrogens for the Earth are a little bit different. Instead of coming in, instead of proteins and polysaccharides, we're now talking about gases. And there are 4 primary gases that constitute greenhouse gases. Carbon dioxide is the most abundant. Methane is not nearly as abundant, but actually accounts for 25% of the greenhouse gas effect in our atmosphere. And it's actually 80 times the strength of carbon dioxide by weight as being an effective retainer of heat. Nitrous oxide is even more so, and hydrofluorocarbons are all over the ballpark, and they're the most rapidly increasing component of our 4 greenhouse gases. These are the forever chemicals. And some of these, especially the perfluorochemicals, are in the environment for thousands of years, 9,000–10,000 years. And they're also many, many times more potent than even methane. So that's what's going to be coming in the future if we continue to produce these compounds. And these are primarily used as, for cookware and for fabrics to waterproof things. And the greenhouse gases arise from the combustion of coal, oil, and natural gas, and primarily go to 4 different areas. We consume about 25% to generate electrical power, then transportation, manufacturing, and finally agriculture, forestry, and heating of our homes and residences. So each of these 4 areas of where these fossil fuels are going, where we're consuming them, what we're using them for, are approximately equal. Now, these greenhouse gases accumulate in the lower part of the atmosphere called the troposphere, and they block the outflow of infrared energy. So instead of when the sun shines on something nice and dark and generates some heat, some infrared energy, it can't get out. So this is very similar. I'm looking at the human body, to our blood vessels contracting, but it's an entirely different mechanism, but it does the same result. Now, it's kind of hard to measure how these greenhouse gases affect our temperature because there's so much variation on planet Earth. First, there's variation according to location, primarily latitude. How far north or south of the equator are you? The surface albedo. Albedo is the reflection capacity of a surface. So an albedo of 1, which is very high, is a lot of reflection. And that's like the surface of the Arctic ice flow. And albedo, a low albedo is like a blacktop parking lot that's been freshly applied. And your feet will tell you, if you walk on ice, very cool. You walk on, during the day anyway, on a blacktop surface, it's very hot. There's a lot of infrared energy that comes out of a blacktop surface. There's also a lot of variation in time of day, of course, daytime being much hotter, the season of the year. And when you look at over thousands of years, we also have to consider the axial precession and tilt of the Earth. The Earth wobbles on its axis. It takes about 25,000 years every time it wobbles back to the previous position. And it also changes its tilt about every 42,000 years. So all of these things are scientifically have to be considered about. Our planet is changing constantly. And then our activity of our planet itself, the volcanoes, how much, sulfur particles are coming out of the volcanoes and into our environment. We look at ocean currents and also air currents, the jet stream. Where is that located? Is it affecting your location? And finally, we come to the human generation of carbon dioxide and the other greenhouse gases. Now, there are a number of scales that the weatherman that you're familiar with. When you look at the AccuWeather or the newspaper, or wherever you get your weather reports, the UV index tells you how much UV light, which is very damaging to your retina and also very damaging to your skin, especially if you're a Caucasian and especially if you're a youngster. So that's a nice, easy scale, 0 to 11 and even higher once in a while. The pollen index, you're all familiar with that if you have hay fever or asthma. The heat index, which is a combination of your temperature and humidity. The fire risk, which also adds wind velocity and the rain forecast, oils, the soil moisture and so forth. But there's no way to specifically tie a weather event that's in a location to carbon dioxide levels or other greenhouse gas levels in the environment. So we've had to turn to attribution science. And originally, we looked at climate attribution. And I'd like to give a woman some credit for this as the originator of climate attribution science. It happened a long time ago in upstate New York. A woman by the name of Eunice Foote was experimenting with sunlight and the heat that's generated by sunlight. And she found, using a glass cylinder and putting it into the open window, that a cylinder filled with carbon dioxide heated up much better than a cylinder filled with oxygen or water vapor. And she published this and presented it in a scientific meeting, the American Association of Science and what?
Concern.
Yeah, something like that. In Albany, New York, not too far away, but she had to have a man deliver the paper. So such was life in those days. Later on in the 19th century, a Swede by the name of Svante Arrhenius, he developed the concept on a more global, instead of using just cylinders in a windowsill, he was thinking globally. And he attributed fossil fuel combustion as a eventual cause. He didn't know that it was currently a cause, but an eventual cause of global warming. And he did publish a paper and presented it himself. And incidentally, he was married to a woman named Carolina Thunberg. And you may know there's a 15-year-old Greta Thunberg from Sweden who back in 2018 skipped school in order to boycott or whatever the Swedish parliament on Earth Day. She's now 20 years old and still doing the same sorts of thing. Then we turn to 1957. Roger Revelle, who was an oceanographer at University of California, San Diego, he was working with a fellow from Scripps Institute named Hans Suisse. And what they did was take the carbon-14 data science that had been developed at the University of Chicago and actually use this to analyze the tree rings. And just counting tree rings, they could count back hundreds of years before Industrial Revolution, before the mid-19th century, when that happened, and up until the current time. And what they said was that, what they found was that the CO2 level had risen as a result of the industrialization of our economies and fossil fuel combustion. And that was also spoken before a House of Representatives, before our Congress, before our committee. he went on from there, and very importantly, during the Eisenhower administration, helped develop the International Geophysical Year. That was 1957, 1958 that occurred. And as a result of that, worldwide temperatures were starting to be collected from cities, and the historical data as far back as these various locations around the globe kept temperatures, mostly high and low temperatures, as well as CO2 readings. And that's when that all started. So we go, it's interesting, the Eisenhower administration contributed a lot to the burning of fossil fuels by the development of our interstate highway system. But also, on the other side, they actually supported the International Geophysical Year. And then let me turn to now to 1988. A scientist, a NASA scientist named James Hansen, testified before Congress, and this is where the alarm bells really started ringing. He made 3 conclusions before this Senate Committee on Energy and Natural Resources. Number 1, Earth is warmer now than any time since instrument measurements began in 1851. 2, with high degree of confidence, 99%, global warming is due to the human generation of greenhouse gases. This was a wake-up call. And finally, he had a proviso. Number 3, greenhouse gas effect increases the probability of extreme summer heat waves, but we cannot attribute a specific weather event to global warming. So there was a big debate between natural variation and rise in temperature due to global warming. And although he could say the planet as a whole was developing a fever, he couldn't say that a specific weather event. And that's where climate attribution science emerged into weather attribution science. And this happened in 2004 when a group from Great Britain, I'll give you the slide, there it is. Excuse me, I should say the United Kingdom, from the University of Oxford and the meteorology office for the country, published a paper in Nature titled "The Human Contribution to the European Heat Wave of 2003." 70,000 people died as a result of that heat wave in 2003. And they said that it is very likely that human influence doubled the risk of the extreme heat wave in Europe in 2003. So this is where collecting a lot of information over a long period of time and throwing it into the computers and analyzing this gave them the confidence to make that statement. And then following up on this, there was an article in 2014 in Nature Climate Change titled "Loss and Damage from Climate Change." And the authors here, both from the UK and Sweden, extreme weather event attribution can be a tool to profoundly reshape the public conversation on global warming. See, until now, the public was just, people were saying CO2 is a greenhouse gas. Well, I can tell you the carbon dioxide level is 421 parts per million. What does that mean? Nothing. I mean, not to most of us. And so there's a group up in Princeton that formed in 2008 called Climate Central. These are climate scientists and journalists, and they got together and they said, they looked at these recent articles and said, we need to develop something that can be used by by everybody, the general public. And they based an index, the Climate Shift Index, on peer-reviewed meteorologic attribution science, some of what we were just going over. And it used both high and low temperatures from over 1,000 locations around the world. And they used historical reference periods dating back to 1851. And the climate shift index indicates how much human-caused climate change has altered the frequency of daily temperatures at particular locations. And it maps the influence of climate change on temperatures across the globe every day. And what they did was, well, let me just show you what the conceptual viewpoint of how you understand the climate shift index. Now, if we look at this graph, on the horizontal x-axis is the temperature scale going from cool to hot, and on the vertical scale are the number of days at each of those temperatures. And you can see, you know, the number of days at extreme heat are relatively few, and likewise at extreme cold. Now, what we've experienced over the past 150 years is a shift of our climate. So now everything is shifted to the right. Everything is warmer. So you can see the red zone. You can kind of look at this, the colors, and then the superimposed sine waves. And you can see what's happening. And what they did was take a particular point for a particular location, and what was historically the frequency of that temperature, and then look at currently what is the frequency and compared those two, and then developed a probability scale between -5 and +5. And the 0 would mean that there's no effect of climate change on the temperature of that particular location. A moderate effect of climate change would be a 1, strong, very strong, extreme, and exceptional. So if you go down to a +5, it means that climate change is the temperature on that particular day is 5 times more likely due to climate change than natural variation. So that's a high probability. So this is basically a probability scale. But it's simply a scale like our UV index. So it's something we can grasp and understand. Let me kind of move through. So if you go to the Climate Central website and put in Gainesville here over on the right-hand side, Gainesville is one of 11 cities in Florida for which there is sufficient data going back, 150 years to actually make a determination. Now, I took my birthday last month, September 20. So I prepared this slide on the 19th of September, and I took tomorrow, which was September 20, and I wanted to see what it showed. And so here's Gainesville. It's a 0. There was no effect. So I had a nice day on my birthday. Now, I didn't need the climate shift index to tell me that, but it's nice to verify scientifically what I was observing myself. And this also goes further than just specific cities around the country. There's several hundred cities which are contained in their index on their website. But they also showed that Gainesville, I'm on a what do you call it, an email list, and now they send me data on what's happening in Gainesville. They're very nice folks up in Princeton at Climate Central. And so what they told me was for the month of August, we were 2.8 degrees above the National Center for Environmental Information normality for a 30-year period, 1991 to 2020. And this is comparing all the data from 1890. That's when Climate Central was able to get accurate data on Gainesville. We didn't go back to 1851. And there are some European countries that go back into the 1700s. You can also see from around the world in the month of July where there were high climate shift index readings. And they did a one-year study. They came out with this index just last year in 2022. They also did a one-year study of where the greatest human impact is for extreme heat events. I'll just lose my. And not surprisingly, Lagos, Nigeria, with a high concentration of population, they had 2.8 billion human days where the CSI index, that scale, was exceeded 3 on the positive sign. So that means they were really roasting. Mogadishu, Somalia, Mexico City, Mexico, these are some of the others in the top 10. I'd like to turn now to tell you where you can get more information and enjoy doing it. If you want to learn about the human aspect of climate change, this is a book that just came out a few months ago by Jeff Goodell. The Heat Will Kill You First. And he has wonderful stories. I don't advise reading them right before you go to bed because you may be too scared to go to sleep. Yeah. But anyway, they're very colorful and well written. And the other book that was published last year by Katharine Hayhoe. Katharine Hayhoe is an astrophysicist out of Texas Tech University. She's a delightful woman. She's an evangelical, and she is proud of being that, and still is one of the major contributors to the climate change science. She is one of the key authors of the Intergovernmental Panel for Climate Change, the IPCC. She is one of the principal authors of their first reports. And she wrote a book, Saving Us. And it's nice, it's entertaining, and it's also educational because she gives references, biblical references of where the Bible is in relation as she unravels the science of global warming. So, and it's an easy read. And if you don't want to read a book, pick up her 17-minute TED Talk. Katharine Hayhoe, and she espouses that the most important thing you can do is just talk about it. And she's also done some work with public broadcasting. She actually has 3 seasons of programs. These are animated, cartoon animated, but she's the narrator of short programs. They last, 7, 8 minutes? 5 minutes, 6 minutes, on topics such as it's too late to do anything about climate change, right? I'm just one person. What can I do? If I just explain the facts, that'll get it right. The Bible doesn't talk about climate change, right? Well, she'll give you the answer. But you can get this on public broadcasting, and it's carried by our local WUFT. So I'd like to open it to questions. And if you want to know how to find more about the Climate Shift Index, go to Climate Central and you can weed through. Thank you, Paul.
Well, please come up here and we'll take turns asking questions. By the way, Allan will stick with us. He's going to continue to talk even after we have to close the session.
Well, just a quick question that may be relative to this or not. We probably all have read about white paint that prevents any heat from getting through that barrier. Is that a good thing or a bad thing for people to think about when they're building or creating, space that we don't want heat to enter?
That's a good comment. I'll give you my personal reflection on that. When I moved to Gainesville in 1975, my wife and I bought a Volkswagen camper. So I went out and it wasn't air conditioned. So what I went out and got some paint that the public schools use to paint the roofs of the buses, which also were not air conditioned. And the school kids seemed to like it. And so we did. We painted the roof of our Volkswagen with that white paint. And we enjoyed that car for about 14 years without air conditioning. That was in the 70s and 80s. So it does work. I can testify. So that's a good thing. White paint is a good thing in the right location.
I gotta say that we had the second Volkswagen bus in Pinellas County growing up in '56, and all of the buses were white roofed.
Good for you.
But that's not my question. When you were talking about the four different gases that are affecting greenhouse gases, can you identify that some of those, like there's some which are easier to get rid of faster than others that can help us with our guidance and asking the governments to take care of reducing some? Because if we try to reduce one that's going to be around for a really long time, but we can reduce the gas of another that can be removed really quickly. Do you have information regarding the, I guess, the life expectancy of those gases in our atmosphere?
Yeah. Carbon dioxide is the most prevalent gas, greenhouse gas, and it's very hard to measure it. It stays in the environment probably anywhere from a decade to 100 or 200 years. No one really knows because it's absorbed by the ocean, and that's what's causing the the increase in acidic capacity in the ocean. But the ocean is reaching its buffering capacity. I'm talking as a chemist, which I haven't had chemistry in a long time. But anyway, so that buffering capacity is now exhausted, and that's why we're seeing damage to our beloved coral heads and so forth, coral reefs. So the carbon dioxide is probably going to be staying longer in the air than it has been till now. But I don't have the true data on that. Now, methane is, let me just think, it stays around about 100 years or so. I don't have the data on top of my mind. And nitrous oxide is longer lasting, several hundred years. And then especially the perfluorochemicals and the hydrofluorocarbon chemicals, they last anywhere from 100 years to 11,000 years. So, and they have also a very potential, for the affecting the retention of the heat on the Earth. So they're the most, although they're the smallest in the number of particles in our atmosphere, that's the quickest growing and also the most dangerous and also the most longest lived. So if there's, they're talking about bringing carbon dioxide, all this technology, trying to put it back in the Earth, back into rocks. Well, that's maybe a good thing for carbon dioxide, but there's not, I don't know how we're going to capture these hydrofluorocarbons. I haven't read of any technology available, but that's the most dangerous thing and the thing that's growing the fastest. So that kind of gives you a little bit of a feel for how we're talking about. These things are going to be around for a long, long time. And that's why global warming it's here to stay for centuries, thousands of years.
Slides back, you had something about the impact based upon
Sure.
I was wondering if greatest human impacts. That was it right there. And you have 2.8 billion human days per year. And so I'm wondering, are these impacts measured according to human density, population? How are these? What does that term mean? 2.8 billion human days per year.
To make that calculation, say there are 10, I don't know the population of Legos, but they just took the municipal, or what's the term for it? I'm not a, well, the urban area, and what the temperature is in that area, times the human beings, and where on the scale each day was it a CS3, CSI 3, 4, 5, and then if it was, they counted that day and then multiplied it by the population, by the 10 million people.
Two figures like this, one on just the human impact and one on where are the greatest impact just on the environmental impact without any regard for human population.
That's a good point. And they haven't got to that point, but this has only been in existence for a year now, publicly. So, and they are constantly building on their technology and on their data. They have a vast resource of data. And so now what they've done is plug in with other organizations like the National Center for Environmental Information. Now, if there is information on plant life, and especially we should be concerned about our ocean temperatures, that can be integrated into their data system and into this same logic.
The point that one of the previous slides, again, you showed the United States and like Minnesota and certain places look like they had the highest rates of change, the more red. And then there were some places that had the least, and some even were like -1 or 2.
Yes, yes.
And so this could be like a good, like, where should we move? Relocate.
Yeah. Yeah. Yes, next question.
I just wanted to mention that asphalt not only is very bad as far as heat production on it, but also emits a lot of noxious chemicals that are poisonous chemicals. I was wondering about a statement that you made earlier, that CO2 is produced in transportation and all that, but then you said the forest, and I don't understand how the forest got blamed for all this. I mean, how did the forest move in? Because usually we're saying that if we've got CO2 taken up by the plants and everything.
Harvesting our forests.
Oh.
Did I not use the word forestry?
Well, I did not.
Did I miss? Yeah, no, they included that as separate from agriculture. We're talking about all the heavy equipment and so forth that goes into it.
Yeah, and then the loss of the forest due to that.
Yeah.
So that's probably what they're talking about. I didn't quite get that.
No, this is just human generated. It's not talking about the balance of how much carbon is absorbed into our forests and by our plants versus how much we generate. Our plants we don't have enough plants in the world to help us out, or enough plants in the ocean.
Any last comment? Question?
This isn't a question, it's a statement. And there's the best thing that we can do, and most of us are beyond this point, but we can have some influence with younger people. to have smaller families. If we cut down on the number of humans, this will greatly help the situation going forward.
Thank you.
Very much, Alan, thank you. What a.
And I want to